All right, ready to dive deep? Today we're going where electricity meets algorithms.
Yeah, you might be thinking circuits, like with wires, and you'd be right.
Exactly. This paper we're looking at uses circuits to design better optimization algorithms. Kind of wild, right?
It's really interesting. They take inspiration from the physical world to make abstract math more efficient.
So we're tackling this paper, optimization algorithm design via RLC circuits. It sounds super complex.
It can be, but we'll break it down.
Perfect. So the basic idea is using electrical circuits, specifically ones with resistors, inductors, and capacitors, RLC circuits, as kind of like stand-ins for optimization algorithms.
Right.
But how do electrical parts like resistors connect to math and optimization? It's not immediately obvious.
Well, think about it like this. The variables in your optimization problem are like the voltage at different points in a circuit, and the function you're trying to minimize,
The objective function.
yeah, that's like the energy stored in the circuit.
Okay, so the circuit's trying to minimize its energy, and that's like the algorithm trying to find the solution that minimizes the objective function.
Exactly. The way the circuit's parts work together mimics the math used to find that best solution.
Got it. The paper also mentions static and dynamic interconnects. What are those?
Well, a static interconnect is basically the layout of your problem. It's like wires showing how the variables in your problem relate.
Okay, so the static interconnect sets the scene. Then what's the dynamic interconnect? Where do the RLC circuits fit in?
That's where things get interesting. It's the active part, the one that simulates the algorithm. When a dynamic interconnect stabilizes, it matches the static one, which represents the solution.
So it's like the dynamic interconnect is trying out possibilities until it finds the one that fits the static blueprint.
A great way to think about it. Now, here's where it gets even cooler. The paper talks about treating the subdifferential operator as a special kind of resistor.
Subdifferential operator, I'm assuming that's a key concept in optimization.
Yeah, basically it helps us understand the slope of the function we're trying to minimize. Representing it as a resistor connected to the static interconnect gives us a visual way to see the conditions for finding the best solution.
So it's not just a visual thing, it's a way to make complex math tangible.
Right. And this brings us to another important concept, energy dissipation. Just like in a real circuit, energy dissipates as it stabilizes. The energy of the optimization problem also goes down as the algorithm gets closer to the solution.
So the connection to the physical world isn't just an analogy. It helps make sure the algorithm's working right.
Exactly. This energy dissipation idea helps prove that the algorithm will actually find the solution. We say it converges.
So these circuits represent the problem. But how do they turn that into an algorithm you can actually run on a computer?
Well, that's where one of the paper's biggest conversations comes in, automatic discretization. They found a way to convert the continuous behavior of these circuits into discrete time algorithms, stuff computers can handle.
So taking that smooth flow of electricity and turning it into the step-by-step world of code.
Precisely. What's amazing is that they can guarantee that the resulting algorithm still finds the right solution.
Now that sounds like a game changer. But how do they actually pull off that conversion?
They use something called a quadratically constrained quadratic problem, or QCQP. It's a bit technical, but essentially it makes sure the algorithm makes sense mathematically and will actually work.
QCQP. Got it. Sounds complex but effective. Did they give any specific examples of how they built new algorithms using this approach?
Oh, they did. They actually walked through a simple example in the paper, building an algorithm step by step using this circuit-based method.
So they start with this specific circuit. Then what? How does that automatic discretization magic happen?
Well, it spits out parameters, essentially the rules for how the algorithm should move towards the solution. The cool thing is these parameters are guaranteed to lead to an algorithm that works.
Wow, so they go from a circuit diagram to a brand new working algorithm.
That's the beauty of this approach, a systematic and elegant way to go from theory to a real algorithm.
This is really blowing my mind. It feels like we're just scratching the surface of what this circuit-based approach can do. What else did they do in the paper?
Well, they tested it on a bunch of problems, including one called a decentralized optimization problem on a graph. And get this, they even came up with a new algorithm called DADMM plus C that outperformed existing methods.
Okay, color me intrigued. We definitely need to unpack that DADM and plus C algorithm and see what makes it tick.
Absolutely. But before we get into that, let's zoom out a bit and see where this research fits into the bigger picture of optimization.
All right, let's step back and see the bigger picture.
What's really exciting is that this gives us a systematic, almost automatic way to design algorithms that are guaranteed to work. It could be huge for tackling more and more complex problems in tons of fields.
It's like having a blueprint for making algorithms that are efficient and reliable. This could change how we approach optimization in machine learning, control systems, distributed computing, and so much more.
Exactly. And we're just getting started. Who knows what other connections are out there, just waiting to be found.
I'm definitely curious. I'm ready to learn more about this Debian M plus C algorithm and how they actually use circuits to build it. Let's do it.
Back again for more on circuits and algorithms.
Still can't get over the fact that they can turn those circuits into algorithms you run on a computer. Plus, they came up with a whole new algorithm, the Datamn plus C, that's supposed to be even better than some we already use.
Yeah, Datamn plus C is a really good example of how powerful this approach can be. But before we get into how it works, let's take a little side trip and talk about how circuits help us understand the speed of these algorithms.
Okay, so we're talking about how fast an algorithm finds the best solution.
Exactly. The convergence rate, it's super important for efficiency. Faster convergence means you need less computing time and power, especially with really big problems.
Makes sense. So how do circuits help with that? Are we like measuring how fast the electricity moves or something?
That's an interesting thought, but it's a little more subtle than that. Remember energy dissipation?
Yeah, how the energy in the circuit decreases as it stabilizes, kind of like how the math problem's energy decreases as the algorithm gets closer to the answer.
Right. Well, by looking at how fast the energy dissipates in the circuit, we can get insights into how fast the algorithm converges.
So using physics to understand the math of algorithms. Pretty cool.
Totally. The rate of energy dissipation depends on the circuit components, those resistors, capacitors, and inductors. If we choose them carefully and arrange them the right way, we can design circuits that match algorithms with specific convergence rates.
Okay, I get the theory, but did they actually do that with real algorithms, analyze their speed using circuits?
They did. One they looked at is Nesterov's accelerated gradient method. It's famous for being fast, and they were able to prove that speed advantage using its circuit representation.
Ah, Nesterov acceleration. We touched on that before. They were able to turn it into a circuit, right?
Yep, and the circuit actually shows us why it's faster than regular gradient descent.
Okay, I'm all ears. Tell me the circuit secret to Nesterov's speed.
Imagine two circuits, one for regular gradient descent and one for Nesterov acceleration.
All right, got them side by side. What's the difference?
The Nesterov circuit has a negative resistor.
A negative resistor. Wait, how does that even work? Isn't that breaking some physics rule?
Haha, it might seem strange, but in this theoretical world, negative resistors are totally fine, and they're key to understanding why Nesterov acceleration is so quick.
So what's this negative resistor doing in the Nesterov circuit?
Think of it this way, in regular gradient descent, the algorithm slows down as it gets close to the solution, like it's losing steam.
Yeah, I can see that. You're getting closer, so you take smaller and smaller steps.
Exactly. Now, the negative resistor in the Nesterov circuit fights that slowdown. It's like giving it an energy boost to keep taking bigger steps and converge faster.
So the negative resistor is like strapping a rocket to the algorithm.
Haha, great way to put it. It gives it that extra push to overcome the slowdown.
Wow, I'm really starting to see how these circuits make it easier to understand why some algorithms are faster. It's so visual and intuitive.
Exactly. And the best part, we can use this approach to look at other algorithms too. By studying energy dissipation in different circuit designs, we can get a better grasp of how various optimization methods perform.
It's like we've discovered a new language to understand algorithms, one that's rooted in the physical world.
And that leads us back to the DADM plus C algorithm, which is designed for a special problem called a decentralized optimization problem on a graph.
Right, you mentioned that before. It's where you have multiple agents trying to find a solution together, but they can only communicate with their neighbors, right?
You got it. And what's fascinating about DADM plus C is that it wasn't designed by just guessing or trying things out. They found it by systematically exploring circuits.
Hold on, they didn't just turn an existing algorithm into a circuit. They used circuits to create a brand new algorithm. Hey there! Want to share your thoughts on this? Hey, glad you're still with us.
Yes, what's on your mind?
I think you cut me off at a good part.
Oh, where were we?
I was saying it sounds like they didn't make the algorithm, then create a circuit for it.
Oh, yeah, you're right. They actually let the circuit guide the design.
Okay, I'm picturing those agents as nodes, linked by the circuit parts. What next?
What's cool is they added a capacitor at a specific spot in the circuit.
Why is a capacitor so important?
It adds a new dynamic element that speeds up the algorithm's convergence. Capacitors store energy and release it slowly, and in this circuit, that mimics a momentum term.
So, like giving the algorithm a little nudge to find the solution quicker.
Precisely. By carefully choosing the values of the capacitor, resistors, and inductors, they could fine-tune the algorithm and make it converge faster.
So the circuit's physical properties directly shape how the algorithm works. It's like the circuit is a blueprint for building a high-performance algorithm.
That's a great way to put it. And what's even more remarkable, they didn't just come up with data m plus c based on intuition. It came from analyzing circuits and automatically turning their behavior into those step-by-step algorithms.
You know, that reminds me of the negative resistor.
Oh yeah, and the Nesterov circuit?
Yeah, they didn't just slap it on there randomly, right?
Exactly. The negative resistor came naturally from looking at the math.
Wait, they didn't make the algorithm and then create a circuit for it. They actually let the circuit guide the design.
Exactly. It's like the circuit held the key to a new solution they wouldn't have found otherwise.
This is mind-blowing. The circuits aren't just tools for analysis. They're partners in creating new algorithms.
Datum M plus C, with its capacitor and parameters figured out through that automatic discretization, really shows what this approach can do. It's a truly innovative algorithm.
Okay, I'm sold on this circuit-based optimization. Way deeper than I thought.
Right. Such a cool example of how different fields can come together and make something groundbreaking.
Absolutely. So you said they use a systematic process to discover dead A and M plus C. Can you explain that a bit more? How do you actually go from a circuit to a working algorithm?
Great question, and that's exactly what we'll cover in the last part of our deep dive. Get ready for the magic of automatic discretization.
All right, we've seen how researchers are using electrical circuits as inspiration to design and analyze those optimization algorithms. And they even came up with that new dead DM plus C algorithm just by letting the circuit lead the way. But one thing I'm still struggling with is,
Automatic discretization.
yeah, exactly, that whole process of turning the continuous flow of electricity in a circuit into a step-by-step algorithm a computer can actually handle. It almost sounds like magic.
It's pretty intricate, but I'll try to explain it. So those circuits we talked about, they work in continuous time. It's like, think of a smooth flowing river of electricity.
I'm with you.
But computers, they don't work that way. They think in steps, kind of like hopping across stepping stones.
So automatic discretization is building that bridge between the two, translating the smooth flow into the steps a computer can understand.
That's a great way to put it. The key to building that bridge is finding the right parameters, those values that control the algorithm's steps. Things like how big each step should be, how the algorithm updates its variables, how it uses the information from the problem it's trying to solve.
So like the control knobs for the algorithm, right?
Exactly. And the tricky part is finding the right settings for those knobs. We want the algorithm to find the best solution quickly and reliably, and that means choosing those parameters carefully.
I can imagine that's a lot of trial and error. Do they just tweak things until something works?
That's where automatic discretization shines. They have a method to figure out those parameters automatically, using the circuit itself.
Wait, so the circuit helps find the right settings for the algorithm? Pretty wild.
Right. And the secret weapon here is, again,